Welcome back, everybody. We finished talking about chapter 18, some basic idea about stars. Now we're going to go ahead and continue forward with chapter 19 with kind of more specific idea about stars. Specifically, we're going to be talking about celestial distances or determining distances to objects in space. Stars primarily, but just objects in space and how far they are away. And this picture that you see right here, starting off our chapter 19 discovery, this gives us kind of a summary, a very quick at-a-glance summary for different methods that we use in astronomy to determine the distance to faraway objects or nearby objects. And some of the methods are very easy and some of the methods are very, very difficult. We're going to touch on one or two of them in this chapter, I think 3 technically. And then we're going to save the rest of them for future chapters when we get there. So the first one here on the far left-hand side, it's one that we really have talked a teensy bit about before in chapter 10. We talked about Venus using kind of radar waves to kind of see through its atmosphere. That same radar can also be used to figure out the distance to these nearby objects, these planets in this case. The reason why this method is useful is that because they're nearby objects, if we transmit radar waves, aka radio waves, towards these planets, it'll take a couple of years for them to travel to the furthermost planets and a couple of years for them to travel back to us, to bounce back to us, like for example with Saturn and Uranus and Neptune. But for a planet like Venus, we send these radio waves to Venus, and within a couple of days they bounce back to us, no problem. So based upon that kind of recognition, then we can kind of use this method to determine the distance to nearby objects. But once you go beyond Neptune and Pluto, the objects are small, they're not very reflective, so us getting the light back, us getting the radio waves back is going to be very, very difficult, if not impossible. Plus, even if there were big objects out there to reflect that light back, it turns out that as light expands, its brightness decreases, its energy content decreases, it becomes dimmer, as we said back in the previous chapters. So there's less light to reflect back, even if the object is very large to begin with. So for faraway objects, this radar ranging method doesn't really work. It really only works for objects within the solar system. If you want to try to figure out the distance to objects like, for example, stars that are nearby us within the Milky Way, then you want to try using this other method that you see right here that we're going to call parallax. So that's what we're going to start off with in chapter 19, is not so much with radar ranging, kind of chapter 10 stuff, but more chapter 19 stuff involving parallax now to nearby stars within the Milky Way galaxy. So how's that going to work for us? Well, it turns out that the heart of parallax, the idea behind parallax, is something called triangulation. And the way that triangulation works is, well, kind of like its name implies, you're basically kind of building an imaginary triangle of measurements and using what you know about that triangle of measurements to calculate an unknown part of the triangle, distance in our case. So specifically for us in astronomy, for us to utilize this technique of triangulation, we need to be able to kind of measure 2 distances and an angle, so to speak. So how does that kind of work here? Well, in this case, if I have 2 locations, A and B, and my goal is to figure out how far away the boat is from the shoreline right here, I can use triangulation with the black lines that you've kind of seen in this case. So I can make a measurement of distance between photographer taking a picture of the boat at point A, photographer taking a picture of the boat at point B, and by kind of knowing that distance, it's really kind of 2 distances that you see kind of right here bisected. But by knowing those 2 distances from A to this point where the boat is located, and then to B where the point of the boat is located, by knowing those 2 distances, and either this angle alpha, which can be measured with a protractor, or this angle beta measured again with a protractor, I can use those distances along with that kind of angle to figure out this distance here that the boat is away from the shoreline in this case. It turns out that this method was introduced by Hipparchus long, long ago back in chapter 2 in the ancient Greek days, the kind of founder of modern day kind of trigonometry, so to speak. And you can kind of see a very simple example of kind of Hipparchus's method done here, in the sense that if our goal is to kind of figure out the distance to the object, aka the tree, the easiest thing to do is to stand at the tree's location, kind of right here, and then move to a different location, point B. And as long as you know the distance between these 2 points and how you had to rotate your camera to keep the tree perfectly in line, by knowing that baseline and that angle, you can actually figure out that distance using a little bit of advanced SOHCAHTOA trigonometry that we have in modern day times. Back in Hipparchus's time, trigonometry was less advanced, more primitive, so more measurements were required, 2 distances and an angle. But with modern day trigonometry, as fancy as it is, 1 measurement of baseline and 1 angle is good enough to figure out distance in this case. But no matter how you do it, Hipparchus's way or with modern day trigonometry ways, the key idea is that with a measurement of baseline and angle, you can figure out the distance to a tree without having to actually cross the ocean or go across the river in both of these cases. And again, this is nice because in astronomy, we can't actually travel to these faraway objects. We can't reach them within a human lifetime. So therefore, the only way that we can find the distance to these objects is by these indirect measurements of distance between 2 measurements and angle of one of those 2 measurements. So we're going to go ahead and kind of look at how this idea of triangulation and parallax together allow us to figure out the distance to a nearby star. And what I'm going to ask you to do is kind of silly, but go ahead and bear with me on this one. Go ahead and close one eye and keep the other one open. Doesn't matter which one, left or right, it's okay. And go ahead and just kind of hold your fist onto your nose, kind of hold the tip of your fist onto your nose and extend 1 finger, your pointer finger, for example. So me, I have my right eye open and I have my pointer finger very close to my face, touching my nose. What I'd like you guys to do is just like I'm about to do, go ahead and now close your right eye and open your left eye as quickly as possible. So blink back and forth, basically. And as you're blinking back and forth, what do you see? Okay, well, I see my finger move. But is my finger actually moving? No, it's still touching my nose. Same thing with yours, hopefully. Your finger is still touching your nose, but your finger appears to move. But look at the background of the screen. When you blink your eyes back and forth, the screen doesn't appear to move. So what we say is that stellar parallax is the apparent motion of an object, a star in this case, relative to a fixed background of other stars, or your computer screen in this case. So how does that apply to this picture? Well, if we have the Earth at this location in January, the baseline measurement is 1 AU, because we said that's the distance between the Earth and the Sun in general. When the Earth takes a picture of the nighttime sky, there's going to be 1 star that's in the foreground, close to our solar system. And there's going to be lots of other distant stars that are further away from us in the Milky Way galaxy that we have as our background distant stars. So maybe in January, as we look at this star here, it's going to appear on the far right-hand side of this photographic plate or CCD image. But if we fast forward in time to July, 6 months later on, and we take that same image, kind of blinking your eye left to right or right to left, then that star's location is now going to be kind of seen on the far left-hand side of the photographic plate or the CCD image. And if you take a picture of the nighttime sky one more time from July, kind of going all the way to January, and if you see that same red star on the right-hand side again, that gives us a repetitive behavior of the Earth going around the sun, but it gives us proof of parallax, the proof that our location relative to the sun and how it changes is affecting our perception of a star's location in the nighttime sky. If we took a picture a third time from July to January, and that red star moved off camera, then maybe that star is just kind of moving with a space velocity through our line of sight. But because that object would have that same picture again in January, the year afterwards, a third time, then that will give us proof that we have a star kind of moving back and forth in this case. And it turns out that kind of with this stellar parallax that we're seeing here in blue, we can use triangulation to figure out the distance from the Earth, the distance from the sun to that star, a very helpful measurement in chapter 19. So how does that kind of work? Well, it turns out that again, using this triangle here on the left, from the sun to the Earth on either direction, January or July, we have a baseline distance of 1 AU. Our goal is to figure out the distance from the sun to that star. So what I really need to figure out is this angle here, kind of called alpha or beta from before. And it turns out that this angle here is related to the angle that the star appears to jump back and forth from far right to left to far right to far left. We can figure out the star's location in terms of right ascension and declination. And our textbook does talk about right ascension and declination again, even though we kind of already talked about it in chapter 2 and chapter 1 to some extent. So go ahead and kind of review the kind of presentation on right ascension and declination a second time. But the key thing is that we can use those angles of right ascension and declination to figure out the angle in the celestial sphere that the star has jumped across. And by taking that kind of total angle and cutting it in half, we have something that's called the parallactic angle. And it turns out that this parallactic angle, kind of the half angle that you see from the dotted black to the solid black, that's going to correspond to this internal angle right here. And that's going to allow us to figure out this idea of the, distance between the sun and the actual kind of star in question. Now, it turns out that as kind of a weird subtlety, this equation is very biased towards the units that it produces and the units that it accepts into its own equation. Specifically, this angle of P, the angle that the star appears to jump as seen on the celestial sphere, it needs to be input in angle of arc seconds. And therefore, the output of the function, the distance d, is going to be in units of parsecs in this case. The equation really doesn't work so well if P doesn't have arc seconds. You can do a kind of translation, you can do a conversion if you want to, but the way that the equation is set up in our book is you find the parallactic angle, the stellar parallax as our book calls it in this case, and plug in that parallactic angle P, and I can tell you within a certain degree of accuracy how far away that star is from the Earth in this case. Now, the one small problem with this method is that it has a bias itself, it has a limitation, and that limitation is basically as follows. So go ahead and repeat that same thing that I had you do with your finger, but instead of holding your finger to your nose, go ahead and hold your finger as far away that your arm can extend, and then blink your eye back and forth. It's going to seem silly, but hopefully no one's watching you, so no reason to be ashamed. But when I blink my eye back and forth with my finger far away, my finger still appears to jump. It's not actually moving, but it appears to jump. But the parallactic angle is smaller. And this is a problem because if the parallactic angle gets too small, then I am not able to actually see the star appear to move. So for example, if you just kind of use that same blinking technique on your computer screen, it barely appears to move at all. So it turns out that this method of stellar parallax, this method of using triangles in very creative ways, it works really well for nearby stars, but its accuracy gets worse and worse and worse for faraway stars until it essentially gives you a value of 1 divided by 0 because your star is now a distant star. There is nothing in the foreground to be measured in the first place. So this method mathematically is straightforward, but it has a very strong bias, a very strong limitation in terms of being able to see the nearby star jump in its parallax. Now, talking about a third different way of figuring out the distance to stars or the distance to faraway objects, we have to limit ourselves to the type of objects that we're referencing in that measurement, something called variable stars. This technique that we're about to talk about does not work for non-variable stars. And I'll talk about how to classify them towards the end of this discussion in the chapter. But the one thing that we're going to say about a star is that a star's luminosity, its brightness, but luminosity is the better phrase because luminosity is objective, brightness is more apparent or subjective. But the luminosity of a star does not have to be constant over time. It can change. A good example of that is think about your metabolism, kind of like how the way that you produce energy. Your metabolism isn't the same at all times in the day. Sometimes you have a lot of energy, you want to go do something. Sometimes you feel kind of lazy and lethargic. You have a very kind of low metabolism in that case. So for stars, their luminosity, their fuel consumption, their thermonuclear fusion, it can change due to very, very complicated internal processes. But the key thing, though, is that if the luminosity changes, we know from the Stefan-Boltzmann law that luminosity, energy output, is proportional to temperature. At the same time, though, if luminosity changes from Wien's law and from Stefan-Boltzmann law, we know that the size of the star can also change. Because if a star's luminosity decreases, that means that gravity becomes dominant because it has less gas pressure, and therefore it will be squeezed to a smaller size. On the flip side, if luminosity increases, the star will want to get hotter. It'll want to kind of bloat in size due to an excess amount of gas pressure. So it turns out that when a star's luminosity changes due to internal phenomenon, then its shape and its color can increase in very, very interesting ways. Now, for variable stars, there are many kind of categories of variable stars. We're going to focus on two of them that have predictable changes in luminosity. Things that are called Cepheid variable stars or RR Lyrae variable stars. What makes Cepheid and RR Lyrae stars special is that the luminosity of the star in question, that luminosity is periodic. Other variable stars, their luminosities change, but not necessarily in a repeatable periodic manner. So this is why astronomers like Cepheids. Their brightness is bright, then dim, then bright, then dim, and it's a nice repetitive change. Same thing with the RR Lyraes, is that they change brightness and luminosity periodically, dim, then bright, then dim, then bright, over and over and over again. So therefore, their behavior is better to understand due to its predictability in changes in brightness, in color, and size. So what we can do is by watching this behavior of periodic brightness for a Cepheid or an RR Lyrae star, we can build what's called a light curve to classify the behavior of that star, and then through a very careful analysis, figure out the distance to that star in a very, very accurate manner. So this picture here, this is kind of a rough representation for any type of periodic variable star, a Cepheid or an RR Lyrae, or some of the more obscure ones that we don't care about in this class. But you'll notice here that this kind of shows us how the size and the color of the star changes. It bloats and it kind of cools down, it contracts and it kind of heats up. This corresponds to low brightness, this corresponds to higher brightness in this case. And what I want you to notice is that the brightness kind of changes in a periodic manner. And it turns out that because of this light curve being periodic, it turns out that what we can do is that, sorry, let me go back to that previous slide. What we can do is that by noting when the star is maximum brightness and maximum brightness, that difference in time can give us the period of this pulsing behavior, this kind of fluctuating behavior of going from big and dim to small and bright to big and dim to small and bright over and over and over again. So by looking at this light curve, we can figure out the periodicity or the period of that Cepheid star behavior or that Lyrae star behavior. And what you notice right here are kind of is a single graph showing us the behavior of what are called delta Cepheid variables. We're just going to call them Cepheid variables for shorthand. And then also here kind of on the far left, we have the variable of RR Lyrae stars as well. Now it turns out that of the two categories, the RR Lyrae stars, their periodicity, the time that it takes for them to go from bright to dim to bright again, is usually less than a day. They're very tricky because their brightnesses change very, very fast. And it also turns out their luminosity, their brightness is much, much lower. So they're hard to see in the first place. So it's not that they're less accurate, but it requires more time to verify their accuracy in the first place. The Cepheid variables, they have periods that can span from a day to almost 100 days in terms of going from bright to dim to bright again. And it turns out that their luminosity is also fairly higher by almost a factor of 10 compared to the RR Lyraes. But this is important for us because what this allows us to do is that by looking at the periodicity of the kind of Cepheid variable and kind of figuring out this idea of how its kind of pulsation kind of changes in terms of brightness, we can work backwards to figure out luminosity. And by finding luminosity of a star, we can go ahead and kind of use this idea of the luminosity mass relationship to help figure out its distance as well. So how does that kind of work? Well, we have to use the HR diagram one more time. And the key thing about the HR diagram here is that if I know where a variable star is in the HR diagram, and it turns out that because its brightness changes, because its luminosity changes over time, then what we can go ahead and say about that is it's going to be kind of moving up and down along something that we call the instability strip of the HR diagram. It's not main sequence, it's not a white dwarf, it's not a supergiant, it's not a giant. It's kind of moving in between the different kind of branches of the HR diagram. The Cepheid variables, they tend to be on the higher side of this kind of HR diagram. The RR Lyrae stars tend to be much, much lower towards the bottom of the HR diagram. But it turns out by kind of knowing where they are on the HR diagram, we can figure out how their luminosity changes, how their size is changing. And again, we kind of see how their brightness changes very, very noticeably. But it turns out kind of based upon that measurement, we can use this idea of luminosity and size at a given moment to help figure out the distance to that star at that given moment. And because these variables are changing in opposite kind of ways, then what we can say about that one is that by finding the luminosity as it pulses very bright, and by finding the size of that star when it's pulsing very, very bright, we can work backwards from the Stefan-Boltzmann law to figure out the distance to that star that's very bright and very, very small, or that's very kind of large and very, very dim in comparison. So the Cepheid variable method, it allows us to figure out the period of a star, how quickly it kind of changes in location, work backwards using the HR diagram to figure out where it is at a single moment in time in the actual HR diagram, and then use that information about luminosity and size to figure out the actual kind of distance to that star in this case. Mathematically, it's tricky because it's a multiple step process, but just conceptually, as an idea, it's very helpful because, again, stellar parallax doesn't work for faraway stars. And these stars, their periodicity can be seen. And just by using a little bit of information about their brightness changing in a predictable way, I can figure out where they are on the HR diagram and then use that to figure out their distance in the HR diagram as well. Now, it turns out that there's one more method to figuring out distance, also involving the HR diagram. It's a little bit tougher because it requires independent corroboration, a second and a third measurement. But if the star that you're looking at is not close by and you can't use stellar parallax, and the star that you're looking at is within the Milky Way galaxy but is not a variable star, then your only option left is to use main sequence fitting. So the way that that kind of works is that the star that you're looking at has to be part of the main sequence. This method does not work for the white dwarf, the giant, or the supergiant branch, unfortunately. But if we look at a star in the nighttime sky and we see its color using our telescope, its peak emitted wavelength, we can use Wien's law to figure out its surface temperature. And therefore, we can figure out if it's an O-type main sequence star, a B-type main sequence star, an A, an F, a G, a K, an M, an L, T, a Y. It doesn't really matter which one. But we can figure out which type of star that it is based upon its color. Now, the question you might ask is, well, wait a minute. There are blue stars that are main sequence, and there are blue stars that are supergiants. How do we tell the difference? Well, go back to the previous chapter. Go back to chapter 17 about stellar classification. A supergiant star will emit more light than a main sequence. And it turns out that really, as you get towards the bluer side of the main sequence, you don't find a lot of supergiants in this kind of far left-hand corner. In the kind of yellow and red area, yes, you do, that's true. But it turns out that main sequence stars, their spectroscopic pattern, their light emission, is a little bit different in terms of brightness and number of lines missing than the spectroscopic profile of a supergiant. A supergiant, because of its temperature and also its size, it tends to emit more light, it has a higher luminosity, and also it emits more colors in general. There's some exceptions, of course, but they tend to emit kind of more light, more shades of blue in their profile because of their larger size. There's more chaos going on within, so they produce kind of a more diverse array of light in the first case. So based upon that kind of recognition from the spectroscopy of a star, if I know that it's main sequence and I know that it's blue, for example, then I know that based upon its temperature being this specific value, maybe 25,000 Kelvin, if I know it's a main sequence and it has a temperature of 25,000 Kelvin, it's got to be here on the HR diagram. Looking to the left, I can trace out the luminosity of that star at that moment in time. And again, by knowing luminosity, I can use chapter 18 to figure out mass. I can also use the HR diagram to figure out size. And by knowing the size and the luminosity of that star, I can use the Stefan-Boltzmann law to work backwards and figure out the distance to that star one last time. So chapter 19 is a relatively short chapter, but the ideas in it are admittedly tricky because they're all basically math ideas about how to calculate distance. Are you going to have to do some nasty calculations involving those? No, absolutely not. But do you have to know how the methods work in general? Yes, absolutely. So for example, O-type stars are very, very hot. If it's a main sequence star, it's going to have a high luminosity, and therefore I can use that luminosity and the size as main sequence fitting to figure out its distance nice and quickly. If I have a variable star, it's easier to keep track of in terms of diagnosis. And as long as I can figure out if it's a Cepheid or an RR Lyrae, I can figure out period, I can figure out brightness and luminosity, I can figure out size and mass, and then I get distance for free afterwards. So just make sure that by the end of this chapter, you're comfortable with talking about and kind of applying, not so much with numbers, but just kind of applying the idea, understanding the process of these kind of three different methods of distance finding. Stellar parallax, aka triangulation, this idea of variable star curve fitting, and this idea of main sequence curve fitting in this kind of chapter 19 cases. That's it for now. I'll see you guys for chapter 22. Sorry, I'll see you for chapter 21, my apologies, afterwards. We are skipping chapter 20 because it deals with dust, and it's a very kind of geology heavy chapter. I'm just going to mention a few ideas in chapter 21 about chapter 20 when we get there.